point about it. Yeah, I think I made the solution right, but it was that very first problem, 2.7, number 6. People put yn equals 1, 2, 3. No, they put yn equals, I don't know what they did. A couple people, I'm not sure. Maybe you should check to see what you'd put. Up to n, then 0. No, they put like this. They put yn equals 1, 1, 1, 1, 1, then 0, 0, 0. Yes, it is on. And then they put, this is 2.7, number 6. Put lecture. And then xn equals 1, 2, 3, up to n, 0, 0, 0. This is to show the range of t not closed, where t from L infinity to L infinity was given by t of C1, C2, and so on, equal to C1 over 1, C2 over 2, etc. Okay. I think people were doing this. Is that correct? What people were doing? Anyway, this doesn't work. Actually, some people didn't do this one. They might have done. If they did this one, this is correct.
Yeah.
Okay, that's correct. Not everybody did. I think maybe this is what people did. This looks correct. This is correct. So you got to be a little bit careful because you have to have yn converging to y. All right. So yn, this one converges to y equals 1, 1, 1, and so on in L infinity. Excuse me, 1, 1/2, 1/3. There are plenty of examples here and go on in L infinity. But if you take the trunk, if you take 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, it does not converge to 1, 1, 1, 1, 1, 1, 1. Okay, you got to be a little bit careful. So you got to make sure that the sequence yn that you pick converges. Okay, in L infinity. I think that I'm not sure if I graded everybody's problem right. I just had the sneaky suspicion maybe I got it wrong. I went back and looked at my notes. I think I'm okay, but you might want to just check it on your own. I don't worry about the points at this point. It was 1 point or something.
Yeah, I think you took up points online because I did that. So I think you did it right. You caught that. But it didn't, you put right on there, didn't converge it.
Okay. Where xn does not converge to x. Excuse me. Xn does not. Let's see. But actually, is this correct? I think this is the correct. This is the problem too, because 1, 1, 1, 1, 1 is in L infinity. So this was incorrect as well because it didn't show that y. It didn't show that. That our range of t is not closed. Okay, this didn't show it, so I needed to do something else. This is still incorrect. Okay. I got yn going to y. But now x equals 1, 1, 1, 1, 1. That is in L infinity. So that y is the image of a point in L infinity. So this is still incorrect. Because x equals 1, 1, 1, 1, 1 is in L infinity. I guess I was being a little bit, I didn't realize that the problem was a little bit too tricky when I was grading it. So I'm pretty sure I graded it incorrectly until today. Okay. So what do you need to do? If you actually look at what did I do, what I did is because there's room for y to still go to 0 as a sequence of numbers. Okay. And therefore converge in L infinity when I truncate. Yet, x could still go to infinity, all right, as a sequence. There's still room by putting in, let's say, a square root here. Okay, square root there, then y is just the sequence of reciprocals of square roots, and then x is this 1, square root of 2, square root of 3, and so on, up to square root of n. Okay, so now this is correct. Because now there is no x in L infinity that corresponds to this y. So here's a point in the closure of the range. Here's a point in the closure of the range. Intersect the closure of the range. Okay. But there's no x that leads to this y. There's no x in L infinity that leads to that y into this mapping. Okay. So you needed to use square roots or something. Basically is what I'm pointing out. Okay. For that problem. All right. Well, now to clear up the mistake. Okay. Other questions about this homework that's coming in, or any other questions about homework that's due in the future, or anything? How are you doing in your homework? Are you being able to catch up?
Well, we're doing it.
What?
I just said, well, we're doing it. I don't know.
You're doing it, yeah.
I'm not always doing it right.
Yeah, well, not everybody gets every problem right. That's for sure. Okay.
You know.
All right. What I want to do now is talk about Theorem 3-3-1, 3.3-1, which is titled the minimizing vector theorem. We talked a little bit about this last time, and it's kind of the core of this section, 3.3. So let's state the theorem and then talk a little bit more about some of the examples we were doing last time. So let X be an inner product space and let M be a convex subset of X that is complete as a metric space in its own right. Under the, I have to be able to talk about a vector space, so I'm going to talk about convexity. And here I'm talking about the metric is the metric defined by the norm, defined by the inner product. Inner product, okay, by dxy equal the norm of x minus y equals the square root of the inner product x minus y with itself. Just to recall all that business, okay? Okay. Okay, so suppose that. What is the conclusion? Conclusion, there exists a unique y, that's the only one, that's the exclamation point, unique y in M with delta equal to the distance between x and y equal the infimum y tilde in M dx y tilde. So there's a unique point in M which is closest to a given x. I'll let x also for any given x belonging to the original space. So just you give yourself a point x. I forgot to tell the vector x. Give yourself a vector x. Give yourself any point in this space, and then you have this convex subset that is complete. We saw last time that that you did need an inner product space for this. The counterexample was last time from lecture 9. You had x equals the closed unit ball B0, 1 in C01. So that's not an inner product space. X is not, M. This is M. It was the closed unit ball in C01, and that's convex and complete. C01 is complete. I have a closed subset of C01. That's a complete metric space. But there were two. And then I took x of t equal to 4 times the absolute value of t minus a half. 0 less than or equal to t less than or equal to 1. Okay, there were two vectors closest to it. You had y1. The distance between x and M. This is another way to denote distance between a point and a set, is just go ahead and write dxm. Okay, this was the delta. The delta was equal to 1, and I had that's equal to the distance between dx y1 equal to dx, and I had two solutions at least. And I guess I could have come up with some more too. All right, and where y1 was identically 1, and I had y2 equals to 1/2 x. Okay, just as functions. Okay, I had those examples. So I had two vectors which were minimizing. Okay. Yeah.
You want to write bigger?
Did a little bit bigger. Okay. Sorry about that. Okay, so I'm going to write bigger. This is a little bit too small. Is this big enough over here? On this side?
A little bit bigger than that.
A little bit bigger. Okay. I got the two boards though. That's good. I'm good. Okay. Yeah. Here's my 2.5 boards. Sorry about that. Okay. So what's the? How do you deal with this? Well, the proof is that in this inner product context, as long as you can get a sequence yn going toward that will achieve the minimum distance asymptotically. So I'm going to choose yn, so the dx yn goes to delta, equals delta n goes to delta. All right. Find the sequence yn in M so that delta n equals the dx yn goes to delta. All right. I'm going to have my x here, and I have my yn here, and this distance is going to be delta n. And get as big as I can. Delta n okay. And what I want to show that the sequence yn is Cauchy. Now I point out that in this counterexample that I gave here before, that's impossible to show. it's C0, 1 because the sequence y1, y2, y1, y2, y1, y2, y1, y2, the alternating sequence, you've achieved the distance delta at each step of the game. Well, so in particular, you've got delta n equal to delta for each n. But obviously, if I had that alternating sequence, y1 and y2 are not equal, that's not Cauchy. There's no limit, even. Okay? Obviously. So it's not Cauchy. So that's impossible in this context. But now it is possible here. So show the yn is Cauchy. How am I going to do that? It's by the Parallelogram Law. It goes like this. Let's draw a ym over here. Suppose that, it means, and so ym is also close to x, and so that's a distance delta m. So this delta n and delta m are not supposed to be very far apart, actually. Okay? They're about the same. They're about delta. Okay? But maybe we take m smaller so that, could be. But these sides are about the same. Okay. Now what am I going to draw for a parallelogram? I'm going to take the midpoint of yn and ym. Well, and so that I'm going to get, I don't know, I guess I can draw this parallelogram. So I'm going to get, so one diagonal is going to be yn to ym. Another diagonal is going to be this other one here. Okay. But what I'm going to do is I'm going to introduce these sides. So these two sides, the delta n and the delta m side. Oops, that's really dark now. Okay. I'm going to make those two sides, I'm going to call them names. All right, instead of the segment, I'm going to call them, put Vn equals x minus yn, and Vm equals x minus ym. Then I have Vn in norm equals delta n, Vm in norm equals delta m, and those are two sides of the parallelogram I have here. Now, let's see, if I average them, I get, let's see, x minus yn is actually, if I put the head of the vector, it's the vector from yn to y, it's yn to x, so this way and this way. If I average those, I'm going to get the vector from the midpoint here to x, okay, which is half one of the diagonals. So if I take Vn plus Vm over 2, that's equal to x minus the average yn plus ym over 2. Okay, which is a point from a point in M. This point is in M. I'll just label it here. Yn plus ym over 2. Because M is convex, there's the convexity coming in. This point here is in M. Therefore, this length of this vector here is greater than or equal to delta. That half diagonal is greater than or equal to delta. But it's also less than or equal to, by the triangle inequality, the average of the norms of Vn and Vm, which is delta n plus delta m over 2. Maybe I should erase this just a little bit. That might fuzz out your computer screen. Okay. Okay. Questions about that? All right. So what we have is that Vn plus Vm over 2, which is that half diagonal length, okay, is greater than or equal to delta on the one hand, because Yn plus Ym over 2 is in M. Okay. Now on the other hand, it's less than or equal to, delta n plus delta m over 2. So it's about delta when n and m are large. All right? So all of these three vectors are about delta. This is just the average of the two lengths, practically speaking. We've got it cornered in there because delta n is very close to delta. Now, what does the parallelogram identity give you? Parallelogram identity says the sum of the two diagonals. What I want to show is that yn is close to ym. What I'm showing basically is that this yn and ym have to be squashed together. This delta is a finite amount. But basically I'm saying that this big angle here is out. This big angle, this parallelogram has to be squashed to a line is what I'm claiming now. Because what I have is that the parallelogram identity tells me that the sum of the squares of the two diagonals is equal to twice the sum of the squares of these two, or the sum of the squares of all four sides. Okay, so 2 times this side squared plus 2 times this side squared. All right, so what I have is that twice this vector, which is Vn plus Vm, right? This is Vn plus Vm over 2, so this is Vn plus Vm. What I have is that by parallelogram equality, I have that what's the idea? Basically, this side is delta, that's delta. I have to have this, I have to have two. Okay, think of this as just delta. Delta squared plus delta squared plus delta squared plus delta squared has to be the sum of the squares of the two diagonals, right? So 4 delta squared is one side of the parallelogram equality. The other side has to be this diagonal squared plus this diagonal squared. Well, this diagonal squared is about 2 delta the quantity squared, which is the 4 delta squared already used up. Therefore, this other diagonal has to be 0, essentially. Okay, then you have 2 delta n squared plus 2 delta m squared equal to Vn plus Vm squared plus the Yn minus Ym. Okay. Therefore, I want to show this is small, so I'm going to put it on one side. Therefore, Yn minus Ym squared is less than or equal to 2 delta n squared plus 2 delta m squared. I don't really need this inequality here. This one I'm not going to use. Not use. I'm just pointing it out. Okay? Minus a lower bound for this, which is 2 delta squared. Okay. The smallest that this Vn plus Vm could be is 2 delta. All right? So I subtract the smallest thing off I could do to get a valid upper bound for this inequality, and this goes to 0 as nm go to i.e. for every, that is, given epsilon greater than 0, there exists a capital N, so that if n and m are greater than or equal to capital N, then the norm Yn minus Ym squared is less than, let's given epsilon squared greater than 0. Okay, less than epsilon squared. Okay, put it that way, something like that. It doesn't really matter at this point. So Yn minus Ym less than epsilon. Okay? So I have a Cauchy sequence. Since, therefore, Yn is Cauchy, and since we have a complete metric space in M, thus there exists a Y in M such that Yn goes to Y. And then what we have is, by continuity of the norm, dxy equals delta. Can I still use the bottom of the board here, Brett? So, by continuity, x minus y equals limit x minus yn equals delta. N goes to infinity. This was just the distance between x and yn, which is the delta n, so the limit is delta. Continuity of the norm. All right, so we have the 1. And now I claim the second part of the proof I've already established by the previous counterexample, because if I had a second one, then I could construct a non-Cauchy sequence that I'd have a non-Cauchy sequence y1, y2, y1, y2, where at each stretch of the game we've actually achieved the minimum distance. All right. So for the previous counterexample, let's say that. And the author goes, he didn't take advantage of that counterexample idea, so he goes through the proof of uniqueness. Okay. If there exists a y2 unequal to y1 with delta equals x minus y1, unequal to y, okay, with x minus y2 equal to x minus y, then the sequence is sequence y2, y2, etc. The sequence, I'll put no parentheses, is at the same time is at once Cauchy and non-Cauchy. Okay, it's not Cauchy because obviously there's no limit to that alternating sequence, and it's Cauchy by the first part of the proof. Alternating sequence. Okay. So that'll finish the proof. All right, so you do have this unique closest point in this case. All right. So the way this is going to get applied is we're going to go to a Hilbert space. So what's the main application? Besides this nice little proof, which gave you the best possible theorem, what's the application going to be? Application is what you're going to take is you're going to take x equal to H Hilbert space, so then you already have a complete inner product space. Okay, and then what should I take? And then I'm going to take simply a closed subspace. M equals to Y equals a closed subspace of H. Any subspace is automatically convex. By closing it, by taking a closed one, I'll have a complete metric space because H itself is complete. So this will give subspace means convex. Subspace gives convex. Closed gives complete by 2.3-1, I think. It's that one. Okay. Any closed subset of a complete metric space is again complete. It was actually in chapter 1, and then we recalled that in the case of norm spaces in 2.3-1. So that's going to be the main application. So what does that give? That gives it gives the following then. If given X in my Hilbert space H, there exists a unique Y equals, I call it capital PX, P for projection, orthogonal projection, in capital Y with the norm of X minus Y equals the minimum. I can call it minimum instead of the infimum now. Minimum overall Y tilde in capital Y, X minus Y tilde. That's dark enough. Okay, so it achieves the delta problem. Okay, delta equals this. Okay? Okay. Moreover, that Y is going to be nice. In fact, what you're really getting in this situation is that X minus Y is perpendicular to all of capital Y. So you have just the situation you'd expect. Here's the origin, okay, sitting in this closed subspace, and here's X sitting somewhere in space, and then you have X, then you have, this is capital Y, here's little y in capital Y, and then here's this residual X minus Y. It's as if you're trying to approximate X by this smaller Hilbert space, right? You have a smaller Hilbert space, maybe even finite dimensional. Okay? So capital Y is itself a Hilbert space. Oh, it's a closed subspace of Hilbert space. So you're trying to approximate a function, let's say, by some other special kind of function, like a polynomial or trigonometric polynomial, what have you. And that corresponds to going to the smaller subspace. So so you're trying to approximate, and then you have the approximation here, and then with this residual vector is Z equals X minus Y. That's going to have the property that it will be orthogonal to every vector in capital Y. Let's check that. How do you know that Z is orthogonal to everything in capital Y? That's the further assertion that I want to make. This is the content of 3.3-2. without writing out the whole thing, because you have it in your book. Okay. 3.3.-2, in this context, in above context, Y closed subspace in Hilbert space, you have that Z equals X minus Y, or X minus this projection of X, is orthogonal to every vector, see what I want to call the vector, Y1 in capital Y means the inner product Z with Y1. So Z is a fixed vector. Y1 is going to be allowed to range over anything in capital Y, so this is going to equal to 0 for all Y1 in capital Y. How do you do that? Suppose not. The idea is this. Intuitively, suppose it's not perpendicular somehow to some other vector in this space. Okay. Then what you can do is take some multiple of that vector that is not perpendicular to. Let's draw another picture. Okay. So suppose not. Proof. Suppose not. So then you've got this vector, this sticker here is somehow not perpendicular to some vector in Y. So here's Y. Okay? I'm thinking of Y as a plane. That's why I'm drawing it this way. Okay? So Z is not perpendicular to Y. 1. So suppose there exists a Y1 with Z inner product Y1 equal to beta unequal to 0. Y1 in capital Y. Okay, then basically the idea is, okay, well then let's take just some scalar multiple of Y1 and make the Z perpendicular to, well, not to Y, scalar multiple. What I want to do is take Z minus, I want to basically take the orthogonal projection onto Y1. Okay, so, and then I claim that I'll have, since I started here at X, okay, here's the vector X, I claim that when I get down here finally, I'll be closer to capital Y than I was before, which is a contradiction. Okay. So, then find scalar alpha so that if I take Z, I guess my scalar alpha, so I'm going to take a little bit of this Y1 away, so that Z minus alpha Y1, take a little bit of Y1 away, all right, so I can get this right angle in here. So the alpha Y1 is going to be right here. Okay. It's perpendicular to Y1. see, that's pretty easy to do just by fixing up the inner products. What you do, you take alpha equal to inner product z with y1 divided by y1, inner product y1. y1 is not equal to 0. Otherwise, you couldn't have inner product with y1 equal to 0. So let's see, if I take this, let's just check it. If I inner product with y1, check that if I take z minus alpha y1 and inner product with y1, that'll be equal to z minus zy1 minus alpha y1 y1. And they define, by the way, I define alpha, then that's just going to be zy1 minus zy1 equal to 0. Okay. Okay, so this is check. Check that I can do that. Okay. So that's been checked. Now, what is that going to give me a contradiction? I claim now, then now I claim that now z minus alpha y1, I better put it up here. Now, but z minus alpha y1, that's x minus y minus alpha y1, right? Because z was x minus y, which is x minus something in your subspace, y plus alpha y1, if you actually take account of it now. I've changed y now by this little itty bit, okay? Alpha y1. We'll have norm less than delta, but we'll have norm less than delta as follows. As follows. So I've got something which is a distance between x and something in y, right? So that's this one. Let's see. I'm just going, but to calculate this norm of this difference here, I'm going to go back to this one to do it. The norm of z minus alpha y1 norm squared equals z minus alpha y1 inner product z minus alpha y1. Now, but z minus alpha y1 into minus alpha y1 will be minus alpha conjugate times 0. Okay. And so this is, if I work this out, equal to norm of z squared by taking z minus alpha y1z. But y1z is alpha bar. So this comes out to be delta squared minus alpha bar equals delta squared minus the norm minus alpha squared. Alpha was not equal to 0. It was beta squared over y1 squared. Okay, which is less than delta squared. Okay, so that's the contradiction. So a little bit of computing with the inner product. Okay, so we have then the orthogonality. Then this gives you all the opportunity to say, okay, let's talk about a direct sum. Okay, not a very difficult concept, but let's go through it a little bit and give an example. and show then that the Hilbert space can be shown, once you have a closed subspace like this, can be written out as a direct sum of the closed subspace plus the orthogonal complement. So now what you'll take is that all the vectors which are perpendicular to the subspace capital Y, that itself forms a subspace which is going to be closed subspace. In fact, Z is not the only vector which is perpendicular to everything in Y. It's just one in particular. It was natural to find, okay, whose norm was this distance problem, okay? But there'll be a whole bunch of other vectors perpendicular to everything in Y, presumably. Can you imagine such a situation? I think you will be able to. But so let's just take an example, okay? Let's take R3, and let's take capital Y to be a line to the origin. That's going to be a closed subspace. Make sure everything here is kosher. Right, simple check. I mean, it's not proving anything is kosher, it's just making sure that we've got at least one example in our belt. So let's take Y3. Excuse me, H equals R3. Real Hilbert space, okay, means real scalars, and Y equals the line, let's say, the set of all T, okay, T in R as a line, X equals Y equals Z to the origin. I mean, why not take the easiest one? Okay. I guess, well, one of the easiest. Maybe it's not the easiest to graph, though. I've got to have that coming out of the board. X equals Y equals Z. Okay. Okay. I guess that's, well, we call it C1 equals C2 equals C3 in our notation. That's terrible. But just pretend for the time. We'll just call it X equals Y equals Z for now. All right? Good old X, Y, and Z axes. Let's go to Calc 3, please. Okay. So that's your subspace Y, capital Y. And now you take, maybe I shouldn't have done that. Okay, take any other point in space and take the, drop a perpendicular to the line. Okay. But obviously there's a whole bunch of perpendiculars to that line. This capital Y, you can think of a plane to the origin that capital Y is perpendicular to. That's going to be the orthogonal complement. So the orthogonal complement Y perp, okay, equals all vectors you can think of a whole, just a whole circle of vectors, right? I mean, just cut this line, okay? So you have a whole, all vectors perpendicular to capital Y, all right, equals the set of all V such that V dot 1, 1, 1 equals 0, okay? I shouldn't have changed the notation, but I didn't want to write C's. Okay. So what would that be? This is the good old dot product, right? Dot product is our inner product. Okay, so how would I do that out? I would say, therefore, I have to have right? Because to be perpendicular to anything in y, here's 1, 1, 1 in y. To be perpendicular to anything, I just have to be perpendicular to that, okay, by scaling. So in general, if I have a basis for capital Y, I'll have a bunch of orthogonality conditions, one orthogonality to each basis vector. Okay. I only have one basis vector for Y. So that would give you what? Just x plus y plus the plane x plus y plus z equal to 0. Okay, plane to the origin, which I could write out as a basis if you like. You can write out a basis for that because you already did that. You did that in your homework for last week. Okay, you did exactly that situation. You calculated the null space of this plane. Okay. Okay. Now, how would so that's y perp. Now, so this is y, and then you have this y perp. Now I claim by take, that you have, you just write out, now I'll have a natural basis for the whole R3 by taking a basis for y, which is this single vector 1, 1, 1, and take a basis for this. Let's see, how did we do that? We wrote this as, the way you normally do it, the null space computation, you take your free variables as the last ones. You can take them as the first ones too. But you take this, you call this an S, and you call this a T. Then you write x equals minus S minus T. You have y equals S. You have z equals to T. This is going way back, right? And then write this out as a linear combination as S times minus 1, 1, 0 plus T times minus 1, 0, 1. So that gives you, maybe it wasn't exactly this example, but that gives you the basis. So the basis of the perpendicular space, y perp, is equal to minus 1, 1, 0, minus 1, 0, 1, which is automatically a basis because of this 1, 0, 0, 1 pattern in the last half of the vector. In other words, they're independent. Good old linear algebra math 313. Okay. So now you have a basis of the full space by putting this one together with these. This one automatically has to be linearly independent of those, because what you have is that this is perpendicular to each of those. Let's see. So that if I take see, is that right? You have to check that if I have that the perpendicularity will imply independence. How do you check that? Okay. If I have E1 equals 1, 1, 1, claim linearly independent of the set E2 equals minus 1, 0, 1, E3 equals minus 1, 1, 0, minus 1, 0, 1. That set. It doesn't mean that this set is linearly independent, though it already is. Okay, what does it mean for one set to be linearly independent of another set? Does anybody remember that?
If you take a linear combination of the basis vectors and set it equal to 0, then all the scalars have to be 0. Right.
Okay. Yeah, in fact, all these three are linearly independent, I guess. So I guess let's just put all these three. We already knew that E2, A3 was linearly independent. And this, we already had a linearly independent set. Well, I'll just claim the whole thing is linearly independent. That's easier to state. Okay? Okay? Well, how do you do that? And I guess this is almost going to be the proof of the projection theorem. Let me see if it is. Okay, I hope it is. Okay, well, just about is. We'll prove it a little bit more here. Claim that this is a linearly independent basis. How would you do that? You would take the linear combination, right? You would take alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, set it equal to 0. What does that imply? Now what I'm going to do is I'm going to inner product both sides by E1. Okay. And so if I do that, I get alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, inner product E1 equal to 0. E2 and E3 by definition are perpendicular to E1. So that implies that alpha 1 E1 inner product E1 plus 0 equal to 0. So that gives that alpha 1 is equal to 0. But now, so therefore, alpha 2 E2 plus alpha 3 E3 is equal to 0. But E2, E3 were already linearly independent. They were a basis of Y perp. E2, E3 already independent. So alpha 2 equals alpha 3 equals 0 as well. QED. Okay. So that's how you could work that out. So what you have is you have so-called direct sum. What's the definition of a direct sum? So let's go to that definition now. A vector space X, this is just for a vector space. Let X be a vector space. This is a definition. Let X be a vector space X equals is written Y plus with the special circular plus Z if is a direct sum of two subspaces. I'm going to write it like this: is a direct sum of two subspaces Y and Z. So Y and Z are two subspaces. If every vector X, if for every X in X we have a unique Y in capital Y and a unique Z in capital Z with X written out as Y plus Z. Okay. And for the orthogonal case, in the above example, Y is equal to the projection of X. Now X, Y, and Z are vectors again. I'm sorry, not coordinates. I should have put C1, C2, C3. Maybe, hopefully that won't confuse you. I'll change it now so that you won't be confused. In our previous example, okay, C1 equals C2 equals C3. Maybe that'll help. This is like C1 axis, C2 axis, C3 axis. Okay, and all this stuff was in vector notation, so you couldn't see any coordinates. Okay, so this was my vector X. Anything in R3, and I projected it onto Y. In fact, you can easily come up with a formula for that with linear algebra. Okay. What the projection would be, some scalar multiple of 1, 1, 1. Y equals the projection of X. And I'm not coming up with the formula here. I'm sure you can do it. And Z equals X minus the projection. Okay? X minus projection of X is like that. That's a unique decomposition. Why is it unique? Where and Y equals the span of E1 and Z equals Y perp equals the span of E2, E3 that we had up there. Okay? How was that unique? So I'm giving you these spaces. We already know that I can do it. All right? We know that I can do it. But why would it be unique? Okay? Indeed, what we have is this. We have is that unicity follows by the computation that if I've got that Y intersect Y perp in this case, or the orthogonal complement is called, is equal to the zero subspace. That's going to be true whenever I have an orthogonal complement. I'm going to always define an orthogonal complement as a set of all vectors that are perpendicular to everything in capital Y. So let's put that over here so you can start thinking in generality. So if I have any subset, in fact, of vectors, if M is a subset of X inner product space. So I define direct sum for a general vector space, but in our application we've got an inner product space. Okay. So I'll go back to the specific example of a direct sum. Define M perp, or the orthogonal, just call it perp, is the set of all vectors Z in X with Z inner product Y equal to 0 for all Y in M. So that's the general definition for this M super orthogonal sign. Okay? It doesn't even have to be a subspace, capital M, it just should be a set of vectors. Of course, then you're going to be generating an orthogonal complement of the set of the space that's generated by M. Okay? It's like it's perpendicular to all the generators of the subspace generated by M. Okay? So think about it. M might just be a bunch of basis vectors. Right? And then it generates those basis vectors generate some subspace. Okay. So you can think of it that way. So I just put this on the side. Note this. Okay? So what I claim is that whenever you've got a subspace, though, in an orthogonal complement, suppose I have a subspace Y in its orthogonal complement, defined by that method, then I claim that's always going to be the zero vector. Indeed, Y intersect, if W is in Y intersect Y complement, all right, then W inner product W is equal to 0. Okay. Okay, it's in both of them. All right? Which implies that W equal to 0. Vector. All right? It's in Y perp means that it's perpendicular to everything in Y. All right? So these didn't even require Y to be a subspace. So those have to intersect in nothing but the 0 element. Okay? So now how do I finish this unicity? So this is, again, another fill in a gap here. Okay? I think the author, when he goes through this, is, he's firing this stuff at you, and then in the midst of the proof he says, this has to be the 0 element. And then you say, what? Double check it. Okay? So here I'm sort of double checking out of order. I'm not being very orderly here. You can see that I started jumping around a little bit. Sorry about that. Unicity follows by this. Why? Let's finish the proof over here now. Erase some of the stuff so that it won't be confusing. How does the unicity now? Suppose so that I can write x equals y. If I can write if I can write x equals y plus z and equals also to y1 plus z1, where the y is in the subspace capital Y and the z is in the orthogonal complement, then by differencing you have y minus y1 equals z minus z1, but y is in y and z is in this, so whatever they're equal to must be 0. You have something in here, you have something in here equal. So there's a common vector equal to v in both of them. So that must be equal to 0. So v equal to 0. Which implies unicity. There's only one way to do it. Okay. I'll go back and say, of course, by the unicity, also y in any direct sum, y and z must intersect only in the 0 vector. Okay, I think I put it in the notes. It's just a minor little computation. Okay, so in the general, can you have a direct sum without being an orthogonal direct sum? Yeah. Just take a plane to the origin and the z-axis. That's going to be a direct sum. Okay? It's a unique way to write something in the plane plus something in the line. Okay? So it doesn't have to be orthogonal. So the direct sum is sort of the general case. There's an example in the notes. Have a look at it. Okay. I think I'll skip it for now. Try to finish this up today now. There's some more examples. Some more lemmas. Direct sum examples. There's a little exercise that I didn't assign, 3.3.2, which is kind of cute. And I calculate the answer by doing an orthogonal projection. Maybe I'll skip that for now since we're really near the end of the hour. I don't want to get into tons of writing. So you have this thing. Okay, let's go ahead and state the projection theorem then to be done. Okay, which I approved in essence, but I haven't stated. Okay, so let's go ahead and have 3.3-4. That'll pretty much do it for this section. There's a little bit more. It goes on and on here, but pretty much the rest of it can be handled with an example. And then we'll be left with 3.4, which I'll have to finish up on Tuesday, which has to do with orthonormal vectors. Well, let's go ahead and have the projection theorem stated. 3.3-4, projection theorem. H equal Hilbert space. Y equals closed subspace of H, then H is written as the direct sum, Y plus the orthogonal complement of Y. Okay. We already showed that you can do this. This is the proof right here. We already showed you could do it. A unicity follows here. This is the proof. Except I'm not putting this. I'm putting Y is Y and Y perp is the orthogonal complement is defined where I just erased it. Okay? Y perp general definition. Z equals Y perp general definition. Okay, and we had already established and then proof this, and we have already established the orthogonality of Z to capital Y, little z, Z in capital Z exists by this little z exists by orthogonality lemma 3.3-2. Okay, we had established that by the orthogonality lemma. Okay, so proof Y equals px, z equals x minus px. Z is in the orthogonal complement. Y perp exists. Yeah, I'll get it right here. By 3.3-2. That was the orthogonality lemma, wasn't it? Let me double check. Yes. Okay. Unicity follows by this computation. Okay. So you have that little theorem. Where we're going to go is we're going to talk about orthonormal sequences. What we want to do is get a nice basis basis for a Hilbert space. And what we do is we start somewhere and we go on. And this is going to be done in section 3.7. We're going to construct the Legendre polynomials, mostly in your homework a little bit. And actually you have to do it already this week's homework. I mean, for next Thursday, February 23rd, you already have to construct the first 3 Legendre polynomials.
There's going to be 10.
No, only 3, and there's already, you're doing it on the interval -1 to 1, and 1 and t are already orthogonal, all right? And t squared are already orthogonal, so you have a lot of orthogonality. Okay, what I'm saying is 1t and t squared are continuous polynomials on the interval -1 to 1, so the Gram-Schmidt process is going to be nearly trivial. So I'm going to make you recall Gram-Schmidt. We're going to fly through it. Okay, I'll do one example. Okay, I think I already did one example somewhere. I don't know if it's in these notes I handed out yet. Yeah, I think I did it with Hermite polynomials, page 8 of these notes. Okay, so have a look if you want to see the Gram-Schmidt process. And because you're going to have that over the weekend, I guess. Okay. And we'll discuss Bessel's inequality when we come back next week. But you may use it, of course. Yeah, Bessel's inequality. These orthonormal bases are going to be nice for, I mean, he gives plenty of motivation in the book, I think. Okay. Excellent. Thank you very much. And again, if you're like pressed for this homework time, just please just give me some notice. Thank you.